Yes, sir, we are live, sir. You can start.
Okay, welcome to our, this is the second live session, right?
Yes, sir, this is the second live session.
Second live session. So let's see, how many of you are there in the first place? I just see Elancherian and Anushri. Is there anyone else online?
Oh, I think only we both will be in the Zoom and other people in
Only
the YouTube.
two of
Other
you,
two.
then Naveen and me. So altogether 4 participants.
Yes, sir, we opened in YouTube also.
Uh,
We are
Oh, I
waiting for
see.
the participants. Yeah, we are waiting for the participants.
oh, I see. And YouTube, how many participants are there?
Only 2.
The one of them will be
I
you.
think one of that is
Yes,
me.
sir. Yes, sir. I'm the one.
One of that is me. Other is me.
Other is you. Okay, then what are we doing talking to each other essentially?
Yes, sir, we'll wait for some time, sir.
Yeah. By the way, did anybody submit questions beforehand like last time?
Like forum
No.
question, sir.
No, sir.
Oh, yeah, forum.
No,
Yes.
sir. We just checked it.
Okay, let's wait
We
for a
just checked
few
the
minutes.
sheets shared. Yeah.
I think around 15 students are taking the exam. So, did you get that information, by the way? Elancherian,
Yes, sir,
Yes, sir.
we got it.
got the information. Around
how
15
many?
students.
15 or?
15. Exactly.
Sorry?
Yes, sir. Exactly 15.
Exactly. So, out of those 15, I mean, at least, okay, anyway, let's see. No, I don't think anyone is turning up. See, it's already 5:22. We were supposed to start at 5:15.
Sir, we'll wait for another 10 minutes, sir. If no one is there, we'll close.
Yeah. Okay, so we might as well utilize this time to get to know each other a bit. Elancherian and Anushri, you are both doing PhD, right?
Yes, sir.
Yes, sir.
So just tell me a bit about yourself. I mean, you had already told me right at the beginning, but just remind me.
Yeah.
What area do you work in? Who's your advisor, and so on?
I did my master's in IIT Madras. Now I'm also doing my PhD here. My guide is Professor Aprameyan. I'm in my first year doing coursework, but broadly the area lies in symmetric spaces. And so yeah.
Okay.
We're just starting.
Symmetric spaces and from the viewpoint of harmonic analysis, right?
Yeah.
That's
Exactly.
what Aprameyan works in.
Yes, sir. Yeah.
Okay. And then Anushri?
Sir, I also did my master's from IIT Madras, and then I joined IISER Mohali for PhD. So I'm working with Dr. Shoma Maiti. And so probably something, so far we have decided to do something along the lines of Riemannian geometry and on 3 manifolds basically. So using 3 manifold topology.
So both of you did MSc together?
Yes, sir.
Yes, sir.
Oh, I see. That's a bit of a coincidence. Maybe not a coincidence. I don't know how you both, NPTEL contacted you both.
Sir, through Dr. Apramayan, so not a coincidence.
Yeah.
I see. So Apramayan knows you both, basically.
Yes, sir.
Apramayan is in
Yes, sir.
University of Madras, is it?
No, he is in IIT Madras.
IIT Madras, yeah.
Yeah. Yes.
I see. So both of you are still doing coursework, first year coursework.
Yes, sir.
Yes, sir.
Yes. Yes.
And do you have some kind of comprehensive exam or something before you start your PhD?
Yes, sir. That comes in June or early
Yes,
July.
sir. For me, interview in August.
Just an interview, no written exam.
Yes, sir. That's what the professor said.
I see.
Format is a comprehensive exam together with an Viva, which is kind of interview.
But how did you get to decide on your advisor at this early stage? I mean, you still have to take lots of courses and so on, right?
Yes, yes.
So, so as soon as you join your institutes, you sort of choose the advisor.
The system here is we have to choose the guide in the beginning. Either we can choose, we can approach guides or they'll allot some guides. That's the system at IIT Madras.
So in your case, did they allot or you approached?
Much earlier I spoke with Apramayan. During my
Okay.
master's also I had some reading courses. So.
Oh, I see. Oh, then okay, that makes sense. Yeah. And what about you, Anushri?
Sir, for us, we are strongly encouraged to approach professors from the first semester itself and maybe approach multiple professors and do some reading courses with them and then decide on some professor before the comprehensive itself. So I spoke to Shoma ma'am at the beginning of the first semester and she agreed to work with me. So that is done.
So what reading course have you been doing?
The first semester I worked on, I studied on geometry of differential forms. So, and then this semester I studied a paper on three manifolds and then
What paper on
had
three manifolds?
Sir, it's on connected sums of like it's on open three manifolds and basically a result on when two open three manifolds are diffeomorphic to each other.
Who are the authors?
Besson is one of the authors,
Oh,
and the other two I don't immediately recall, sir. Those are difficult.
oh, okay. I got it. Yeah. I see.
I think we have got a student,
Rashmita Hore.
Rashmita. Yeah.
Okay. Yeah. So yeah. Any questions? Since you are the only student, and there are three people waiting for you to ask a question. So please go ahead.
Sir,
Tell me.
sir, this is Rashmita.
Yeah.
Sir, I have submitted 2 questions on Google form.
Okay.
I also have another question.
Actually, can you tell me the questions you submitted on the forum? as
Yes.
well. Yeah, whatever you want.
Okay, sir.
Hmm.
Sir, I wanted to ask that does there exist some manifold M on which any closed K form will be exact and that for all K?
For all K.
Any closed K form on this manifold will be exact for all K greater than equals to 1.
Yeah, certainly. I mean, the manifold, if you don't assume compact, then it's very easy. You can prove that on, for example, Rn, Euclidean n space, then any closed form of any degree will be exact. And in fact, not just Rn, if you take any open convex set in Rn, the same proof will show that the result is still true. That on any open convex set, any closed K form will be exact.
Okay, sir. And if can there exist some K such that any closed K form on any manifold is exact?
On any manifold,
Yes. Can there exist such a K such that any K form on any manifold on any closed K form on any manifold will be exact?
no. Why should, I mean, there's nothing special about the K. Certainly not true that there is a single K. In fact, if you can show that, for example, if you look at the n-dimensional torus, S1 cross S1 n times, then you can show that there are closed forms of every degree between 1 and n, which are not exact.
Okay, sir.
So, and in fact, you can even calculate. Yeah, right. It's not difficult to show that. For example, if you just take S1 cross S1, the two-dimensional torus, then there are one forms, and there are two forms which are close but not exact.
Sir, I wanted to understand that extra what extra properties are required on these forms, so along with being closed, so that they become exact.
No, it's actually not a property of the form, but it's more like what is a property of the underlying manifold, which will force a. Of course, it is possible that a given closed form can be exact due to for some specific reasons, but generally the question one asks is what property does the manifold, what properties should the manifold have so that every closed form of a certain degree is exact, for instance. So it's a property of the manifold, not of the forms. Like I said, it may be possible that on a given manifold, for example, that there are closed forms which are not exact, but there are always certain closed forms which are exact. In a very easy way, you can get those. But just by looking at a form, whether you can decide whether, looking at a closed form, whether you can decide whether it's exact or not, there is no nice way of finding that out. There's no computational way, some practical way of finding that out. On the other hand, if you insist that all, not just some, all closed forms are exact, all degree k closed forms are exact, then there are criteria for deciding which manifolds have this property that all closed k forms are exact. There are criteria which can be actually implemented. So this basically goes on to the realm of topology. So the way it proceeds is this stuff that whether a closed form is exact or not is, it turns out, even though it seems to involve differential forms, smooth structure, and so on, actually, surprisingly, this turns out to be a property of the topological space, not about the smooth structure. So it is something which is even if you forget about the smooth structure, just the topological, look at the topological space, you can decide whether every closed K form is exact or not. So this is the famous theorem which equates this differential form stuff leads to what is called Dirham cohomology. On the other hand, there is something which can be constructed just using the topological structure called singular cohomology. So the theorem is that Dirham cohomology groups are isomorphic to singular cohomology groups. And the thing is, the point is that something which is purely topological is always, in principle, easy to compute. There are lots of techniques for computing topological invariants like fundamental groups, singular cohomology groups, and so on. While something which involves a smooth structure and forms is more difficult in principle. By the way, you can always, as you know, you can always construct closed forms which are exact just by taking a lower degree form and taking d of that. So if you want a closed K form which is exact, it's almost by definition. It's just start with omega to be a K minus, any K minus 1 form. Take d omega. That will by definition give you a closed form which is exact. But your question is, if you start with a closed form, how do we decide whether it's exact or not? That there is no practical answer for that. Anything else?
Sir, could you explain? I want to understand the geometric meaning of this orientation on manifolds. What does it represent geometrically?
Geometrically, yeah, it's clear enough what it represents. When one thinks about orientable, one always has this standard example of something which is not orientable, namely the Mobius band, Mobius strip. Are you familiar with the Mobius strip?
No, sir.
Yes?
No, sir. I don't.
No.
I know what it is, but I don't know the definition.
Okay. You know what it is, at least pictorially, right?
Yes, sir.
Yeah. Well, fortunately, the Mobius band can be regarded as a submanifold of R3. It's a two-dimensional submanifold of R3. And the definition, actually, the definition is in your assignment, right? One of your assignments. Or did you change the problem?
No, sir, is there.
No, sir, it is there. It is
Oh,
there.
because you couldn't change, right? Or was it the last homework or the one prior to that?
Last week, sir.
Last. Oh, so you could, yeah. So your definition of Mobius band was wrong, by the way. The quotient, the identification map is not
R minus 0.
Yeah, yeah. No, that were T and I think minus T should be taken. Anyway, the point is that the Mobius, if you know what quotient topology is, you can define the Mobius band as a quotient space. But then you have to show it can be embedded in R3 if you want to visualize it. But there are other ways of defining the Mobius band as well. Whatever it is, it can show that once you have a definition, you can show it's a manifold without much difficulty. Two-dimensional manifold. In fact, as I said, it's a submanifold of R3. Now, that is something which is not orientable. So what makes it non-orientable? We know that if you take a circle which traverses the length of the Mobius band, or maybe I can draw a picture actually. Yeah, let me share screen. Yeah, can you see the screen? Yeah, I'm going to try to draw the Mobius band. So it comes well. What did I do? I did something which is not quite accurate. Okay, so the twisting has taken place at this. Now, the thing is that if you, let's take the central circle here. And let's start with a two-dimensional as a basis of the tangent space. Remember that I said that it's a submanifold of R3, so you can, everything is sort of very concrete. The tangent space is a subspace of R3. Of course, when we draw the tangent space pictorially, we don't draw it as a subspace, but rather as an affine subspace, which passes through the given point. So, yeah, I take a basis. Now, you sort of let's move along this dotted circle let's regard it as a parametrized curve, and let's move along the curve and just transport this in a intuitively parallel way. All this can be made precise, but if I do that, so for instance, here at this stage, it will be continue to look like this. Now, next, basically, I'll end up going back. So at that place, it will look like this. Oh, actually here itself, sorry, yeah, the crucial thing I forgot. So when the twist takes place, this would have already, this up would have gone down because of this twist here. So by the time I come back here, the horizontal one will be okay. The vertical one will be down at this point after I traverse this circle. So the point is that now what is going on here? Well, It's in fact, this curve definition here, I just took a curve. This curve definition can be made precise, in fact, that on a manifold, one can define orientation in terms of curves, but one would also need a Riemannian metric actually, if one wants to carry this out. But the idea is that there should be some consistent way of, if you're at a point in a manifold, there should be, and if you have tangent vectors at that point, you should be able to say which basis is positively oriented, which basis is not. So for instance, in R2, of course, it's always confusing because Rn is confusing because the tangent space and the manifold are the same. But let's think of R2 and let's take this point, my point under consideration as the origin 0, 0. The tangent space is again R2. And we have a well-defined notion of when a basis is positively oriented. So if this, for instance, E1, E2, this is an ordered basis actually. So I should use, this is positively oriented. While, for instance, if I take minus E1, E2, this is minus E1 and then E2, this would not be, this is not positively oriented. So positively oriented in this case would mean that the second vector is obtained from the first one by rotation by counterclockwise by 90 degrees. I think second, yeah, that's right. Counterclockwise by 90 degrees. So that gives a sense of, yeah, which one is oriented, positively oriented or not. So the thing is, can we do this? So what we want is, on a manifold, let's start with an abstract manifold. At every point, and if, the tangent space at that point, I should be able to talk about a positively oriented basis. Given a basis of the tangent space at any point, I should be able to decide whether it's positively oriented or not. So this is already creates problems as and of course there is something more to say, which is that this notion of positively oriented sort of how to say this, it should be sort of very continuously from point to point. I mean, what I mean is, for instance, if you go back to the let's just go to R2. At 0, 0, I've taken this E1, E2 to be positively oriented base. Now, if I'm close enough to 0, 0, still the tangent space, this should be positively oriented, E1, E2. I don't want suddenly at this point, I don't want to declare minus E1, E2 to be positively oriented. 0, 0. If you look at the tangent space, so this is P, P, R2. For this, I've declared E1, E2 to be a positively oriented basis. Now let's take Q to be, I just change it slightly, epsilon, 0. Since we are in R2, all the tangent spaces are just R2 itself. So, but I don't want things like to declare this to be positively oriented. So this notion of positively oriented should be somewhat natural in the sense that, I mean, visually it's clear enough that if you're close enough to one point, the basis should not suddenly change. So with that small condition, continuously changing notion of positively oriented, we can ask whether it is even possible or not. The point is, in the Mobius band, it's not possible because of this problem. If here I've declared this to be, if I declare the standard one to be positively oriented, throughout the circle, if I do this, I'll be continuously changing the basis. So it should continue to remain positively oriented, this parallel way of moving it. But by the time I come back to the same point, I get something negatively oriented at the original point. So therefore, it's not possible. That's the conclusion. So in short, oriented just means that at each point in the tangent space, you have a notion of a positively oriented basis. And this notion of positively oriented basis should not jump from point to point. It should vary continuously. That's it. And this vary continuously, all this, whatever I said in terms of basis can be made precise. It's not difficult, but quicker way of stating the same thing is what I did in the class. Either you can use coordinate charts and declare compatible charts, or you can just say that there's a non-vanishing n form on the manifold. By the way, the non-vanishing n form especially gives you quickly this notion of positively oriented n form. If you have a omega n form on the manifold of dimension n, omega p is not the zero form at any p. If I have this quickly enables you to decide, get hold of this positively oriented basis, notion of positively. What you do is, for any x in M and a basis so let's say you have a basis of the tangent space TP M. Declare this one. Again, this is an ordered basis. I should not use curly brackets actually. To be positively oriented, if omega, now what was the point I used, x or p? Did I take x? Okay, p. If omega p, just plug it into this n form. Now, the point is that this is a non-vanishing n form. That means it's not the zero form. So that would mean that the moment so you can check that if you have an n form on a vector space, n-dimensional vector space, which is not the zero form, the moment you plug a basis into that, you will get a non-zero number. It's just actually the determinant more or less. So, but the thing is that it can be either it can be positive or negative. We want it, if it's positive, we call V1, V2, Vn a positively oriented basis. Otherwise, it's not. So the existence of an N form gives a clear-cut notion of positively oriented basis. And one can show that sort of continuously varying choice of positively oriented basis will also can give rise to an N form. So that is the geometric meaning. Well, that's not the geometric meaning, one way of looking at it.
Okay. Sir, may I ask another question? May I ask another question, sir?
Yeah, but you have to speak a bit. Your audio is not very clear.
Okay, sir. Is it audible now?
Now it's better. Yeah.
Sir, we have been doing n-dimensional manifolds in this
Yeah.
course. I was thinking whether there are infinite dimensional manifolds or something.
Yeah, there are. I mean, for example, this just like Euclidean space. See, manifold. After all, what is a manifold? It's something which is locally homeomorphic to an open subset of Rn. That would be an n-dimensional manifold. Now, instead of Rn, suppose you take this definition: a topological manifold of any infinite, potentially infinite dimension. Instead of Rn, you just take any vector space of any dimension, any Hilbert space, any Banach space. So you just demand that locally they are homeomorphic to open subsets of a. Of course, you have to be a bit careful when dealing with infinite dimensions. I mean, not all infinite dimensional spaces are isomorphic. So you have to fix a. So you have to say, you get a notion of a manifold modeled on a fixed Hilbert space or a fixed Banach space. So as you change the Banach space, you will get different notions of manifolds. That is, of course, and also I'm just talking about topological manifolds. If you want to make sense of smooth structure, then you will have to talk about the transition functions being smooth, but that is not a difficult thing. It's differentiability of smooth functions between Banach spaces. You can use the same definition that we used for the definition of derivative in Euclidean spaces, a linear transformation and so on. Without any changes, the same definition works. In fact, in Kumaresan's book on Introduction to Smooth Manifolds, or no, what is it? It's called a course in differentiable manifolds and Lie groups or something like that. He deals with, when he talks about derivatives, he just deals with abstract vector spaces, not necessarily Euclidean spaces. So differentiability of functions or maps between infinite dimensional spaces is not difficult to define. It's the same definition that one uses. And therefore one can talk about, but And these infinite dimensional manifolds are extremely useful actually, especially in partial differential and solving partial differential equations and things like that. They play a very important role. But from the geometric point of view, what are of more interest are finite dimensional manifolds.
Okay, sir. Thank you.
Okay. So Rashmita, if you have any more questions, you can ask. Otherwise, we can end it now, right?
Sir, that's all the questions I had.
Sorry.
That's all the questions I had.
Okay. So, by the way, where are you studying?
Sir, I am doing MSc second year from Pondicherry University.
From?
Pondicherry University.
I see. Second year of Masters.
Yes, sir.
In what subject?
Mathematics.
Math.
MSc in mathematics.
Mathematics. Okay. I missed. Oh, so do both of you know Rashmita, Elancherian and Anushri?
Yes, sir. She has been like one of the like performing consistently well. So we know her through the course.
Oh, know her through the course. Okay, good.
I think I might also know her. I don't know. Like there are a lot of my juniors who are studying in Pondicherry. So
I see. That's what I thought.
Some, yeah.
Yeah, I meant in that sense. I see. Okay, that was an interesting discussion. So let's end it now, right?
Yes, sir.
Okay then. Bye.